How does a computer work?
Why can you program in languages such as C? Different types of computers.
Why people claim that computers only understand zeros and ones.
We will see that there are some general applicable ideas and principles that have produced the amazing technology behind the microprocessors that support the many digital devices we enjoy today.
One of those general ideas is called the von Neumann architecture, or Princeton architecture. This is a computer architecture published in 1945.
Yes, most computers today, more than 70 years later, are organized as the von Neumann model.
Under the von Neumann architecture, an electronic digital computer has the following components.
First, a processing unit. Second, memory, and finally input and output mechanisms.
These may seem obvious, but further, the processing unit has two main subcomponents.
The arithmetic logic unit, with processor registers, and a control unit that includes an instruction register and a program counter.
The arithmetic logic unit, abbreviated ALU, is where operations, like adding two values, happen.
The control unit is what decides which instruction to execute next and whether such instruction is an addition or some other operation.
The memory stores data and instructions. The data and instructions are treated the same as a major aspect of this design.
Von Neumann architecture now refers to any stored program computer. Instructions and data are in the same place, in the memory, so they're both represented in binary, with zeros and ones.
Thus, instructions and data need to be encoded to be stored in memory. Instructions are named with equivalent integers, so internally computers do not have a name for adding or subtracting, they have a number for each.
Since specifying an instruction is providing its code, sometimes people refer to programming as coding and to the programs as code.
To execute or run a program, the computer, iteratively, retrieves from memory the next instruction. The program counter is a special register that indicates which instruction is next.
That is, the program counter holds the address, or position, in memory where the next instruction must be fetched from memory into the processing unit, and it lands in a special register called the instruction register.
Once the code for the instruction is in the instruction register, the circuits of the control unit extract information, in particular, what is the instruction and if there are operands or data.
The process of recognizing which instruction is to be executed is called decoding, and corresponding signaling wires transmit this to the ALU.
If operands are required, this usually are registers of the processing unit or addresses in memory to bring data into registers of the CPU.
When all data and signals have been collected, the control unit indicates that the instruction is ready to be run. The ALU is activated, and results are placed again in the processing unit registers.
Some instructions involve copying back results from processing unit registers to the main memory.
The repetition of these two phases is called the fetch-execute cycle because the machine first retrieves from memory the necessary instruction and its operand, and, in the second phase, it executes the instruction.
Because the memory must provide data and instructions, it receives the name of read memory, and because it must store results, it is a write memory.
Because the addresses to retrieve instructions or data are scattered over the memory, it is also called random access memory.
Moving data or instructions from RAM to the processing unit, or out to RAM, is much slower.
Typically, the processing unit could run its fetch-execute cycle many times while data is retrieved or stored in RAM.
But since the mechanism needs the next instruction from RAM, the processing unit does idle while this happens.
The speed issue has been named the von Neumann bottleneck, because it often limits the performance of the corresponding system.